In this video, we're going to deduce the structure of C10H12O2 and introduce a new functional group to you. So, here we have our NMR as we do in all these videos, and we're going to look for what we have to start with and then go through what we don't have. We have 2 oxygens here, really important to notice. So between 6 and 8 we have our benzene, and the benzene has 5 protons on it, which means it's mono-substituted. We have a CH2 here, a CH2 here, and a CH3 here. Notice triplet, triplet, and a sextet. Now we'll talk about the sextet in a second. Okay. Now let's look at what we don't have. So we don't have a carboxylic acid. So 2 oxygens straight away, you need to look for a carboxylic acid. There's nothing there between 10 and 12, which is indicated on your data sheet. There's nothing here between 9 and 10 for an aldehyde, and there's no alcohol. You can't see a small singlet with a 1 by it. Okay, so no alcohol, no aldehydes, no carboxylic acids. There is also highly unlikely that it's a ketone because you've got 2 oxygens and you don't normally have 2 ketones in a molecule. Let's do the table and let's put everything in the table. So we've got everything in the table. Let's do our environments. So we've got 4 hydrogen environments from the 4 peaks. And let's look at this sextet. And that's a really important thing for this. The sextet means you have 6 peaks, n plus 1 equals 6. 6 minus 1 is going to be equal to your number of adjacent hydrogens, which is 5. So we have 5 hydrogens on the adjacent carbons. It must be carbons because you can't have 5 hydrogens on a single carbon. Okay, so if we then go across here and we look at this, we've got a signal here, okay, that is a CH2. Now if it was surrounded by a CH2 on its left and a CH3 on its right, so you had CH2, CH2, CH3, which is a propyl group, this CH2 in the middle would have 5 hydrogens. 2 plus 3 equals 5 for 5 hydrogens on the adjacent carbons. So I think there's a propyl group there as well. But let's go through this simply first. So we have a CH3 because of the relative peak area, CH2, CH2, and a C6H5. We then check it against the full molecular formula, and it leaves us with CO2. So that suggests we have an ester because we have 2 oxygens left and a carbon. Okay, we know we haven't got the carboxylic acid. We know we haven't got any of the other functional groups. So I think this is an ester. But let's put this up to the side and start going through it. So from there, we had decided that from the CH2 and the CH2 and the CH3 must be a propyl group. So it must be CH2, CH2, CH3. Okay, so we've got that propyl group. And that's because if that is the case, and this was bonded to something here, okay, that this would be a triplet because it has 2 adjacent hydrogens there. This one would also be a triplet. Okay, and this one, because it has 2 hydrogens there, 3 hydrogens there, 5 hydrogens, would be a sextet. Okay, so it's a sextet. And they would have the relative peak areas of 3 and 2 and 2, which is what we have up here. So we have 3 and 2 and 2, 3, 2, 2. We have triplet, sextet, triplet, triplet, sextet, triplet. Okay, so this is our propyl group. We also know that we have a benzene. Okay. And we know that is mono-substituted. And we've got to connect these somehow, and we know we've got CO2. Now this is where the problem arises, okay? So, and there's a really important lesson that you have to learn from this. Esters can go in 2 ways. So basically we could have an ester. Let's put the ester in the middle. We can have an ester like that. Okay. Or we could have an ester like this. Let's put our CH2, CH3, and then swap the ester around. And so you can see the ester can be this way or this way. And this is the difference between full marks and 1 mark, or full marks, 1 mark. Okay, so basically you will lose a mark, is my point. Okay, if you get this wrong. So how do you get it right? So all we have to do is we look at our datasheet. So our datasheet has two different ppms. So if you look here, a hydrogen on a carbon connected to an O is 3 to 4.3. A hydrogen on a carbon connected to a C double bond O is 2 to 3. So they're two different ppms. So all you have to do is look down here and go, right, okay, where's one of mine? Is any of mine in those regions? Okay, so therefore, this one that I've got right here is in that region, okay, and it's in this region down here. Okay, so it's in that region. That means that CH2, okay, and that CH2 is this CH2 here. Okay, so that CH2 is a triplet, so it's a triplet, it's 2. Okay, and that, in this one, it is bonded to the C double bond O. So of these two, which one do you think is correct? Well, the answer is, it is the one where the CH2 is connected to the C double bond O. So the correct one is this one here. Okay, so this is our correct one. This would still get you most of the marks in the exam, but this is the correct one because you're looking at this CH2 here. Okay, it comes out at 2.3. 2.3 is in that region, 2 to 3, where the hydrogen on the carbon is connected to a C double bond O, where this hydrogen on the carbon is connected to a C double bond O. Okay, and so it's this way around, and it's this isomer that you will create. Now, just to finish off, we want to go back to the table. So we haven't included any more detail on here. Okay, so first of all, we know that that sextet is bonded to a CH3. So let's put the CH3 on. There you go. It's bonded. It's unambiguous now. We've put a section of our molecule, and then we know that this CH2 is bonded in this version here, because this is the correct one, okay, is bonded to the C double bond O. And so I put that in there. So what I end up having is a unambiguous table, and I end up eliminating the wrong one, okay, and I'm just going to do that for you right now and just say, right, okay, let's get rid of the wrong one. There we go. Which leaves you with the absolute correct one at the bottom and the correct isomer. So just to finish off this analysis, I just wanted to show you what it looks like with the other isomer, what signal you will get. So the other isomer is where the CH2, and you can see this CH2 here, is bonded to the O, the single bond O. If it's that, 3 to 4.3. We didn't have that, we had it at 2.3. So we had this isomer down here where the CH2 is bonded to this CO. Okay. Now, to summarise, if there are two oxygens, then always check for the carboxylic acid peak. There's no peak between 10 and 12, it's likely to be an ester. And it will look just like an alcohol peak does, slightly wider at the bottom with a 1. Now, depending on whether the signal comes out between 2 to 3 or 3 to 4.3 ppm, changes the structure of the ester. So remember, these two signals come out these different areas, and it's really important that you recognise that they are there, because it will change whether your ester is one way or the other. Now, if you put both of those in conjunction with each other and you use the taking away all of the different sections away from the molecular formula, then I'm sure you can get all the esters right in the future.